Howdy. The purpose of this video is to give you 3 examples of the use of limit properties, which we talked about today. We're going to walk through a simple example, a medium example, and then one example that's also easy but might be intimidating at first. So let's consider the limit as x goes to 2 of x plus 2 over x minus 4. We look at this and we want to identify which of the limit properties would apply here. And we notice, first of all, what we have are 2 groups that are divided by each other. And so that suggests that indicates that we want to use the quotient rule. But we have to first check. We need to check that the bottom limit here does not go to 0. And that's a nice polynomial, a linear function in fact. And so therefore, we can evaluate that limit mentally with direct substitution. Our thought bubble over here says that the limit is going to be equal to 2 minus 4, which is negative 2, which is not 0. And so we can use the quotient rule to say that this limit is the same as the limit as x goes to 2 of x plus 2, divided by the limit as x goes to 2 of x minus 4. And off to the side, we're going to indicate which limit property we're using. The limit of a quotient is the quotient of limits. And then each one of these top and bottom limits will now be further evaluated with limit properties. And in this particular case, the top limit is the limit of a linear function. And so I can evaluate with direct substitution. 2 plus 2 is 4. And the bottom one is also a linear function, so I can again evaluate with a linear function. And off to the side, I'll just put a linear function rule. And there it is. Notice that this is a perfectly good number, and I do not need to simplify it. I can if I want to. Sometimes my inner nerd can't help himself. Let's take a look at a second example. The limit as x goes to 1 of the square root of 4 plus 2x squared minus 4x cubed. Here I look at this and I ask myself, well, what function is going on here? I have the square root of a bunch of things. And of course, a square root is a fractional exponent. It is x to the 1/2. And so I'm going to treat it as an exponent and write that the limit of the square root of blah, blah, blah is the same as the square root of the limit. And that is appealing to the power rule for limits. Now, I examine this function right here, and I see that it is made up of the sum and difference of 3 different terms. And so I can use the sum rule and the difference rule. It's okay to use both of those rules at the same time. Sum and difference rules in order to rewrite that limit. And now I consider the first limit. The first limit is a constant, and therefore I can simply evaluate that using the constant rule. The second limit requires a constant multiple rule application, and so does the third limit. So that's the constant rule for the first limit, and then the constant multiple rule for the other 2. And then finally, we once again have the power rule. The limit as x goes to 1 of x squared is the same as the limit as x goes to 1 of x squared. And likewise, x goes to 1 of x cubed. And we've finally gotten ourselves down to a nice linear function so that we can evaluate with direct substitution. So that gives me 4 plus 2 minus 4, which is the square root of 2. And we're done. Now, those of you who have already done the reading will recognize that all of these steps right here are covered by a powerful theorem that we prove in the reading. The handout on the polynomial and rational function theorems gives you a wonderful shortcut so that you could, if you know that shortcut, come to the answer of square root of 2 much, much faster. That's an advertisement for doing your reading, by the way. Let's consider a third limit. It's posed in the form of a question. It goes like this. If the limit as x goes to c of f of x is equal to k, and the limit as x goes to c of g of x is equal to L, then what is the limit as x goes to c of 3f of x plus g of x squared? And here we look at this, and our first thought is they got rid of all our numbers. But then we realize, no, K and L are numbers. They're just numbers whose values we don't know. So there's no problem here. We simply have to use the limit rules as we did previously. So we look at this quantity and realize that it is the sum of two terms, 3f of x and g of x squared. So we can use the sum rule for limits. Say that the limit of a sum is the sum of limits. Notice that it's no problem that I don't know what c is, and it's no problem that I don't have numeric values for k and L. And then, for the first limit here, I can use the constant multiple rule. Oh, I needed some rule. That's the step that got me from here to there. So I can use the constant multiple rule to rewrite this limit as the limit as x goes to c of f of x. But for this one, I'm going to appeal to the power rule. To rewrite this as the limit as x goes to c of g of x quantity squared. So we have the constant multiple rule for our left-hand limit, and we have the power rule for the right-hand limit. And finally, I know what this limit is because the problem originally told me that this limit is k. So I replace the limit with its value, which is k. And likewise, I know what this limit is, which is L. And so I replace that limit with its value, which is L. And I'm done. I get the value, I get the evaluated expression 3k plus L squared. I hope these three examples help clarify how we use limit properties in order to simplify and evaluate limits.